Earth Climate, Part 5. We shall talk now about the solubility constant of ferric hydroxide, because as you remember from earlier parts in this talk, iron is one of the limiting nutrients required to allow the algae to live on the ocean surface. And when they are capable of thriving on the ocean surface, the algae can take the carbon dioxide to the ocean bottom. But there are some things about the properties of ferric hydroxide that you need to understand if you're planning on dumping ferric sulfate or any other iron compounds into the pelagic seas. Now here's the slide that explains the solubility constant. On the first line you see the FeOH3, and then it's got the sub S, which denotes that it's a solid. And then on the right hand side, when it dissolves, if it does, we have ferric ion in the water. That's what the sub AQ means. And then we get 3 hydroxyl ions. So then, to define the solubility constant, we take the molar concentration of ferric ion and the hydroxyl ion to the 3rd power, and experimentally it's been found that that equals to 2.79 times 10 to the minus 39 molar. So then the other thing we need to know is the concentration of hydroxide ion. Well, we know the ocean surface water has a pH of 8, and water, when it dissociates, goes into hydrogen ion, which is always hydrated, of course, and hydroxyl ion. So then the product of those two is found to be 10 to the minus 14th power. So, going down to the next line, then pH 8 means that hydrogen ion concentration is 10 to the minus 8. And if we solve that previous equation for hydroxyl, we get the hydroxyl concentration at pH 8 is 10 to the minus 6. So then we solve the second equation, since we know what the hydroxyl concentration is now. We can solve that for what the dissolved ferric ion concentration will be. And there it is on the 3rd line from the bottom. We have 2.79 over 10 to the minus 39 over 10 to the minus 16. sorry, 18, because 3 times 6 is 18. And so then we just subtract the exponents, and we find that the molar concentration of ferric hydroxide in equilibrium with the suspended solid ferric hydroxide is approximately 2.8 times 10 to the minus 21 molar. And now to put that in perspective, Blaine finds that the minimum iron concentration required by the algae to absorb carbon dioxide or to even stay alive is 0.09 nanomolar, which translates to 10 to the minus 11 molar iron in the water for the algae to survive. So you can see that if you're just going to dump something like iron sulfate in the ocean, which many people have done, the only reason it works at all is that there are some natural iron complexing agents in the ocean. And if you're going to intentionally put iron in the ocean, then one of the things we ought to consider, which is on the lower left-hand corner of the screen, is ethylene diamine tetracetic acid. And that's a strong complexing agent. And in fact, it's present in all shampoos and things like that. So it's used in large quantities at the present day. So there we explain why some of the people who went around dumping iron sulfate into the ocean is not very profitable. Thank you.